This video is going to continue on the idea of derivatives. Now, in the last video, I went over how we can kind of create a special function that would represent the instantaneous rate of change for a function. And that is exactly what a derivative is. It is a function that represents the slope of another function. So if, in terms of notation, if f of x is a function, then f prime of x, which is just this little notch here, is its derivative. So how do we find the derivative of a function? As I mentioned before, in the last video, I showed you how to use rise over run to find a derivative. And this should be familiar to you. This is basically just the updated rise over run equation that we created that introduces the property of limits to rise over run to help us solve rate of change. So if this section right here is unfamiliar to you, don't worry about it. Head back to the previous video on rates of change to familiarize yourself with it, and that'll help you to better understand what I go over in this video. Now, what I mentioned is that doing this approach with this equation can be quite tiresome. It can take quite a lot of time. So what we actually prefer to do is follow some core derivative rules. So if somebody asks you for a proof of a derivative, that most likely means that you're going to need to use this equation to show how we can derive the equation. But if you just need to quickly solve for a derivative, or in other words, f prime of x, we're going to follow some core derivative rules. And let's look at a couple of those right now. Rule number 1, if f of x equals c, where c is a constant, then f prime of x equals 0. That is called the constant rule. And I will visualize that on our straight line right here. Let's say that this is the equation y equals 3. So really, we have a y value of 3 constantly across, no matter what our value of x is. And so we can think of it as taking the derivative of 3. That would have to be a 0 based on the constant rule. And that makes sense because the slope of this line is constantly 0. All right, fair enough. Second derivative rule. If f of x equals x to the n, where n is a real number, then f prime of x, or its derivative, equals n times x to the power of n minus 1. And I am going to help you visualize this with these two graphs over here. So let's say that this is y equals x squared, and that's our parent function of the quadratic. So if I follow the power rule, this 2 is going to drop down in front of the equation as a coefficient, and then our exponent is going to be decreased by a value of 1. So I'm just going to rewrite this as f of x equals x squared. And so if I find f prime x, or the derivative, I'm going to get a 2 times x to the 2 minus 1, which is just going to be 2x to the power of 1, and we can kind of ignore exponents of 1. Now, what that means is the equation 2x represents the slope of x squared. And this is actually a graph of 2x. So what you'll notice is as we take the derivative of a function, the derivative is going to be to a degree lesser than the original function. So here we have a degree to the power of 2, and here we have a degree to the power of 1. And let's say I have f of x equals 2x. If I were to find the derivative of this, it would be 2 times 1 x to the 0, which would just be a 2. Which makes sense, as a straight line in this case will have a constant slope. So if you can put together these two derivative rules, there's actually quite a lot you can do with polynomials. And what we're also going to do is combine some of the algebraic properties that we went over in the first video. Those properties that maybe we didn't think were super useful are actually quite useful now. Let's look at the first example here. F of x equals 3x squared plus 4. So before I get into the derivative rules, let's think about the algebraic properties of limits. We learned that when we're adding or subtracting two different terms, we could technically consider that as two different functions that we're working with. So let's treat this as f of x and this as g of x. So basically what I'm doing is I'm solving for the derivative of this plus the derivative of this. So let's look at 3x squared first. Now, I know how to deal with exponents. What about this 3 over here? We can actually apply another algebraic property, which was the coefficient property, where I can basically pull out any number that's in front of my variable and basically ignore it until the very end. So what I could rewrite this as is 3 times the derivative of x squared. The derivative of x squared is going to be a 2x, which we already went over before. Then we just have to remember to multiply this by 3, because that was taken outside of our derivative. So our answer here is a 6x. So that's this first part here. Now let's look at our second part. We know that from the constant rule, the derivative of a constant is just going to be 0. So really the second part of this is just a 0. Therefore, f prime of x of our original function is just going to be a 6x. Now, as you get familiar with the derivative rules, you're not going to need to break down things so step by step, like in terms of pulling out a 3, and then applying the rule here, and then applying a separate rule here. You're going to quickly be able to combine these rules and solve for a derivative. So I'll show you how I do that here. We can separate all 4 of our terms and look at them one by one. Let's look at the 5x to the power 4. I know that my exponent of 4 needs to be brought down in front and multiplied, but I can just go ahead and multiply that with the 5 and get that out of the way. Then the 4 needs to be brought down a degree, so instead of to the power of 4, we're going to be to the power of 3. Now I move on to my second term. I'm going to bring down the exponent here, multiply it by my coefficient, so negative 3 times 3 is a 9, and then once again, I need to lower the degree of the term by 1. In this case, we technically have an x to the power of 1, so if I bring this down here, I'm still going to be left with a 1 over 2, because 1 over 2 times 1 is 1 over 2. And then I'm left with an x to the power of 0, which we can kind of ignore, because that's just going to equal a 1. Finally, we have a negative 6. The derivative of negative 6 is just going to be 0, so really I can ignore that. So our answer, or the derivative of this function, is 20x cubed minus 9x squared plus 1 over 2. All right, things are getting a bit more complicated. Now we have an equation that has multiplication between two terms, or two bracketed terms. And in this scenario, we have a couple of options. Option 1, we're just going to expand our brackets and then apply our usual rules. Number 2 is to follow a different derivative rule, which is known as the product rule. Let's look at option 1 first. So I'm going to rewrite the equation here. And when we are expanding terms like this, we just have to apply this term each time to the individual terms here. So kind of like this. And then do the same with our second term. So expanding all of this out will give us 2x cubed minus 6x squared minus 10x plus 3x squared minus 9x minus 15. And if I collect all of my like terms, I'm going to get 5x cubed minus 3x squared minus 19x minus 15. So at this point, we now need to apply our derivative rules, just like we did with the example up here, because we basically set up a very similar equation. So let's apply the derivative rules. 5x cubed is going to turn into a 15x squared. 3x squared is going to turn into a 6x. 19x is going to turn into a 19. And any constant by itself will just be a 0. So that is one way to find a derivative. But you may have noticed that this takes quite a while. And also, as you move on to deal with more complicated functions, it would take even longer. So what we could do is think of this equation, or function f of x, as a multiplication of two other functions. So really we could say g of x times h of x. And when we're dealing with multiplication, we can't actually go back and follow the limit property that involved multiplication. We are going to need to follow a different rule, and that is the product rule. And what it tells us is that the derivative of a function with this sort of setup is going to look like this. Now don't worry if it's a bit confusing, I will go over this slowly. So what this is showing us is we're basically considering our original function as multiplication between two other functions. So to find the derivative in this scenario, we find the derivative of the first chunk of our function, multiply it by the second half, and then do the opposite here, where we have our original g of x and we multiply it by the derivative of h of x. So let's use our example up here to better visualize this. Again, let's consider this its own function and this its own function. So for the derivative of f of x, I first need to find the derivative of g of x. So if I just look at that on its own, 2x, if I find the derivative of that, it would just be a 2. And then we can always ignore constants by itself because that will be a 0. So the derivative of g of x is just a 2, but then we multiply it by the entirety of h of x. Then, the second half of my derivative, I have g of x on its own, the original g of x, times the derivative of h of x, which h of x being h squared minus 3x minus 5, so that's going to give me a 2x minus 3. So just like that, we were able to solve for the derivative of f of x. Now it may not look as clean as option number 1, because in option number 1 we already distributed all of our terms and sort of expanded it. But usually when we're working with derivatives, we just want an equation to work with. So we have an equation that we can plug in x values and solve for the instantaneous rate of change of a function at that value. And that's the most important thing. I am not going to go over the proof of the product rule in this video. Most proofs, when we talk about derivatives, are going to circle back to our updated rise over run equation. If you are a student that really likes understanding where equations come from or rules come from, if you are a student that really likes to figure out how we find these rules with proofs, feel free to look up the proof for the product rule. I am thinking about doing another video that goes over some derivative proofs just to give you that extra bit of info if you're looking for it. So I'm still thinking about that. Anyways, thank you for watching. Hopefully this was useful as an introduction to quickly finding derivatives of equations. The next video will be going over some other derivative rules, namely the chain rule and the quotient rule. So if you'd like to keep learning about other derivative techniques, please stay tuned for the next video.